In the previous video, we took a look at an early tape operating system called Cutter. It was created by Processor Technology to work with a series of boards they made for early S100 computers like the Altair or this MSI 8080. It would load from cassette tape into your computer, and you would specify here on the sense switches the address at which you wanted it to be located. That way you could put it into the highest RAM possible based on the amount of RAM installed in your system. That's a pretty slick solution because 8080 code is not position independent, so they had to do some work to relocate it as it loaded to the address that you specified here on these switches. Now later on, Cutter was much more readily available in EEPROMs, and it would be installed in another board that Processor Technology would make called the GPM board. But what I found most interesting was this early version booting off of tape and with that relocation capability. And as mentioned in the title of this video, it was basically a lost tape. I haven't been able to find it. And so I thought it would be an interesting project to try to recreate that boot tape. And we demonstrated that tape working in the last video. In the video today, we're going to go ahead and talk about how we made that tape and how it works. Fortunately, we don't have to start from scratch in trying to recreate this boot tape. The boot process is the same as all early Altair or MSI software was. The first thing you have to do is toggle in a bootstrap loader on the front panel. That gives the computer just enough smarts to then begin reading the tape. The first thing it reads off of tape is a second stage, more powerful loader, whose job is to then read the final payload with error checking and that kind of thing. Or in the case of loading Cutter, not only does it do error checking, but it also relocates Cutter into whatever address you specified on the front panel sense switches. Now in the manual is where you'll usually find the bootstrap loader. So here is the loading and executing Cutter instructions. Here's the bootstrap loader that we entered on the front panel in that last video. So what we can do is disassemble this code to get an idea as to what is expected on tape where the second stage loader is. It'll give us our first hints of what that second stage loader has to look like. So here's the disassembly of that. Again, I didn't write this code. This is the actual disassembly of the code. And again, keep in mind that the goal of this code was, of course, to do its job, but then also to be as few bytes as possible so that the operator didn't have to toggle in as many bytes on the front panel. So there's a few tricks that are played in here. So this does start at 0, just like we saw. All these bytes right here are generated by the assembler. These are the actual same bytes as the bootstrap loader shown in the manual. So this is a one-for-one match. All right, so the first thing it does is it loads the HL register with 40 hex. This is the address where the second stage loader is going to be loaded. And you can see down here, after it's all done, it jumps to that code by doing a transfer of HL into the program counter to do the jump. And that would have the hex 40 in it that we loaded up here at the top. Save a byte, rather than loading the stack pointer or something else, it just uses that as the stack pointer. So the stack will go down from 40. It then also puts 40, that same 40, into B and C, which will both get used later as well. We'll see that in a minute. All right, so then here it turns on the tape. Remember, we saw it automatically start the tape, and we go into this 3-byte loop that I called skip 64. It just reads 64 bytes from tape before it moves on. Now it does this restart 4 instruction, and it uses this as a 1-byte subroutine call. It's meant to be used for interrupts, but if you're not using it for an interrupt, it's a way to get a 1-byte subroutine call, which saves space. So down here at hex 20 is where restart 4 will always go. So this is our subroutine to read a byte from the cassette. So it's in a loop waiting for the flag to go true to say that there's a byte available. And you can see instead of doing an AND immediate with some bit mask, I'm doing an AND immediate with L. That's not a 1. I'm doing an AND with register L. And register L has a 40 hex in it from before, 40 hex being the tape data ready bit mask. So that's why 40 hex was used, is we're getting multiple uses out of it to try to reduce the number of bytes you have to toggle in. So anyway, every time you see a restart 4, that's getting a byte, returning it in A. So this is decrementing B, which is 40 hex or 64. So we're doing this loop 64 times to skip the first 64 bytes. Now when this loop is done, the 16-bit register BC, which is a combined register, will now have 0 in B and 40 in hex. So BC, when this is done, now also has 40 hex in it, which is the load address. So HL has 40 hex and BC will have 40 hex after this loop is done. So next it waits for sync being a 0, 1, and I could determine that by this code here. This code will loop forever until the byte returned from reading the cassette is a 1, because if you decrement 1, you end up with 0 and this loop exits. So on the tape, we know we've got at least 64 bytes of something. Then we have to have any number of bytes that are not 1 until we get a 1, at which point the actual second stage loader has to follow, because it then falls into this loop where it's going to load the data in and store it starting at 40 hex. So we get a byte, stored in indirect B. B has 40 hex, increments B, so it's just going to keep going up in memory. Then it sees if the byte that we just stored is a DD hex. So obviously the terminating character is a DD. This works because DD is not an instruction in the 8080, so you're not going to run into it, and they just coded it to make sure they did not have a DD anywhere in their data. So basically the tape looks like this in the beginning. It's got at least 64 bytes of leader that's not a 0, 1, and then the byte immediately prior to the second stage loader is a 0, 1 that says start loading. We then have the second stage loader, which starts loading at 40 hex. That's where we're going to have to org the second stage loader. And it can't have a DD in it, but then at the end, it needs a DD to mark the end. Once it gets that DD, then it just jumps to it. All right, so that's the entire bootstrap loader. And at this point, we have jumped to the second stage loader. All right, so next we're going to take a look at the relocating loader, the second stage loader that I created. I can't guarantee it's identical to the original, but it's got to be very close because it works with the exact same instructions that are in the manual. It works with the exact same bootstrap loader, and it works with the exact same version of cutter. So it's got to be pretty close to the original, even though it may not be identical byte for byte. All right, so what this bootstrap loader has to do that's the most difficult is it has to relocate cutter as it loads it. 8080 code is not position independent. That means somehow we have to know what bytes are address bytes and have to be changed. Now we're only relocating the upper byte of any address. We're not worrying about the least significant byte, just the upper byte is being modified. And this is the exact same problem that they had with CPM. And CPM created something called move CPM, and it used essentially a bit map where you had one bit that represented each byte in the payload. So I'm calling that a relocation table. It has 1 bit per byte of the module being what we're loading, a generic name for the code we're loading. In this case, it's cutter. So if you had 2K of cutter, which we have here, we're going to have a relocation table that is 1/8 that long because we have 1 bit per byte. So the relocation table is 256 bytes. And if a bit in the relocation table is a 1, then that is a corresponding byte that does need to be relocated. And to relocate a byte, all we really need to do is add the value of the front panel sense switches to it if we have orged our assembly at 0. And I'll show you what that means in just a minute. All right, so hopefully I can make this all clearer as we go through this. So the module length is basically the length of cutter. It's 2048 bytes, 800 hex bytes. The length of the table is 1/8 of that. This works as long as it fits in a byte, which means this code, semi-generic, it can only load 800 hex max the way I did it. All right, so comment here is a leader of over 64 bytes that are not a 1 must precede this code on tape. So it wasn't easy to put those bytes in because I'm starting here at 40 hex and I need to go to like a negative address to get that many bytes in. So I manually put those in later, and we'll see that process later on. All right, so at 1 prior to the start, I've put the 0, 1 start byte. Remember, that's what tells us to start loading. And then from then on, we've got the actual loader itself, and it keeps loading. There's no DDs in that until it's completely done. And at the end of this, I put the DD, which marks the end of the loader. So here we have the entire structure that we saw loaded by the bootstrap loader. All right, so let's go ahead and take a look and see how this works. I have a checksum every 256 bytes. First thing I'm going to do is load the relocation table. So I do a get byte routine, store it in memory, and loop until I've read the number of bytes required. Then I get the checksum and make sure it matches, and if it doesn't, we jump to an error routine that matches what the manual says we do, and I'll talk about that in a minute. All right, then it goes and it looks at the front panel switches. That's in from FF, and it makes sure that what's specified is a valid address. It's got to be over 200 hex in memory, and it's got to be F400 or less in memory as well. And if that's not correct, then we have an address error, and it jumps and again generates an error in the same manner as described in the Cutter user's manual. So the next is the actual work of this, and we do it by looping through the 256 bytes of the relocation table. And for each byte of the relocation table, that's going to move 8 bytes of payload. Again, because each bit represents 1 byte in the payload. And again, this is the same basic procedure that was done with move CPM in CPM. So we load that byte, we test a bit. If it's not set, we just go on and move the byte. If it is set, then we read the offset value. For example, we did 34, and if the most significant byte in a 0-ORed Cutter was 0, it would add it and put in 34 instead of 0. Or if the leading address was a 0-1, you add 34 to that, then it would end up at 35. And so this then loops through the 8 bits of each relocation table byte, and after each one of those, then it goes through and grabs another byte from the relocation table to do another 8 bytes of actual data. Now, every 256 bytes of actual data, it's going to do have a checksum. So it gets the checksum, validates it, and continues. So that's the whole process, is to loop through each bit in the relocation table, move the corresponding byte into RAM, adding the value of the sent switches to that byte if it's a relocatable value, meaning it had a 1 in the relocation table. And when we're all done, then it's all exactly where it needs to be, and all addresses have been modified. Now, once it's loaded, we're going to halt the machine like we saw in the video. But prior to halting the machine, we need to put a jump instruction down at 0 to wherever we loaded it. If you remember, all we have to do is hit reset. And this is, again, code I've put in here, but it's to match what the instructions say it will do. So we put a jump instruction at 0, and then we pull the load address, which I had on the stack, and store it at 0-1. So I just formed a jump to, for example, if you had 34 on the sent switches like we did, this does a jump to 3400, and that starts the Cutter. So it puts that into memory, and then it turns off the motor, and then it executes the 8080 halt instruction. Now, if we had error conditions, we didn't demonstrate this, but basically if you have a checksum error, when you hit reset after the halt, it's going to immediately halt again, so you know that something was wrong. You then reset and stop the machine, use the front panel to examine location 1 and, location, is it 0 or 1? Location 1. 0 is the halt instruction. Location 1. An error code of 1 means a checksum error. Error code of 0 means an address error. And that matches what's in the instructions. Other than that, the only thing we have is a routine that gets the byte from tape each time. That routine does an update of the checksum as it does that. All right, and then after the end of this is where we actually put that relocation table and keep the checksum. All right, so that's the whole the bootloader that does the relocation on the fly. Now, the question is, how did I come up with that relocation table? Well, to do that, I took Cutter, which people have recreated the source for this. We have both by disassembly and by somebody typing it in. And by default, it's usually here at C1000 because that's where it runs most of the time when it was distributed in ROM. All I have to do is take an assembly here at C1000 and then turn around and org it at 0 instead and reassemble it again. And then I have 2 files that I can compare, and anywhere where they're not identical has to be something that changes on relocation. And then I just write out a bitmap that represents all those locations where these 2 files differ when compiled or assembled at C or when assembled at 0. Well, how did I magically make that bitmap table? Well, interestingly, I created let's go ahead and take a look at it. I created a utility for generating move CPMs for any CPM BIOS you might write. It's here under miscellaneous software on my website. Here's make move. So make move makes a move CPM for any CPM BIOS you might write. And the way it does it is by taking two different assemblies, say one at 32K, one at 48K, just like we did one at C1000, one at 0. It finds all the bytes that are different and writes out a table. So I basically just hacked my little move CPM program, or my make move CPM program, to generate that table for me. I only have to do it once, so it's not like I needed a really fancy utility to do that. So at that point, I now have the relocatable, I have the relocating loader that we wrote. I have the relocation table written. And by assembling this at 0, I have the version of cutter I want to put on tape, because if I org it at 0, all I have to do is add the front panel switches to end up with the actual address. So now all I need to do is combine all this stuff and put it onto a tape somehow. And we'll take a look at that next. At this point, we have everything we need to make the tape. First thing on the tape will be that second stage loader. I also call it the relocating loader. That's this reload.bin. Next on the tape, following the loader, will be the relocation table. That's this reload table.bin. That is the table that has a bit per byte in cutter that's going to have to be relocated. And then finally, I have a cutter orged at 0, assembled at address 0, as that cutter 0.bin. And at this point, I figured I would just open up a hex file editor on my PC, pull these all in, and make the tape. But then I remembered I had to compute the checksum every 256 bytes on the data following the relocating loader. So I decided I'd go ahead and make a program. I made this makecuttertape.c, which will bring all this in, compute checksums, and then write it all out. And it just runs under a command prompt, good old-fashioned style. Let's take a quick look at that. It builds the entire tape image in memory, and this image pointer is going to keep track of where we are. First thing I do is I create the leader that we need. If you remember, we need at least 64 bytes or more, and it can't be a 1 because 1 signals the start of data. So I chose to use AA. So I write 80 bytes of AA. Then next we open the relocatable loader binary. Go ahead and load that in, update the image pointer by the length that we just read. Next, we load the relocatable bitmap table and read that in. And now I update it by 257. Its length is 256. I verify that here. I update it by 257 because I need to make room for the checksum. Starting with the relocation table and then all cutter, we need a checksum every 256 bytes. So here I open cutter 0 and read it in 256 bytes at a time, incrementing by 257, incrementing the pointer. And again, that's to leave room for the checksum. All right, so after that's done, I go back and compute all the checksums every 256 bytes and stick it in. And then at this point in memory, we have a complete image of what that tape should look like. So I can open and write cuttertape.bin with just one write statement. Now, while I had this all in memory, I decided I'd go ahead and write a version of it that would work with the 3P+S serial board. So instead of reading from the cassette tape, it would read from a serial port. That way I could do some easy testing at a higher baud rate, and also anybody who wanted to try this could do it, even if they didn't have a cassette interface. And this requires just patching 2 locations in memory. So it's a pretty simple change, and that's just the 2 places where it's accessing FA and FB, which are the I/O addresses of the tape player, and we replace it with 0 and 1. Looks like I have an extra 0 in there I didn't need, but that still works. And at that point, I write this 3P+S version of it. All right, so you just run that program under a command prompt, and it creates the tape we need, which is this cuttertape.bin. We take a quick look at this in a hex editor. You see the first 80 bytes here are the leading AAs that I wrote out. Here's the 01 sync byte that starts it. So this right here is the start of the relocating loader. And it runs all the way up here until you get to DD. Remember, the DD signaled the end of the relocating loader. So then everything after this is the bitmap and cutter. So here's your bitmap. It's 256 bytes. Here's the checksum for it. Here's the start a cutter, and on. All right, so at this point, I have got an image of cutter tape ready to go, but I don't have a tape. So how do I make an actual tape? Well, that I'm going to have to do on the target machine, meaning I'll take my Altair with a cuts board in it. I need to send it this tape image somehow and have it in memory, and then have that program write that out to a tape using the cuts board. So I created this program here called Write Tape. This is 88 assembly. This is running on the actual machine with the cuts board in it. Let me open up the version that's been assembled, the listing file. Code entry point is here at 100. So I jump to 100 hex, and it then prompts me to go ahead and send that binary image through the console serial port. So obviously my console is a terminal emulator running on this PC. Now, to be safe, I go ahead and clear out any garbage that might be in there. And then at this point, I use D to point to the binary image in memory, and I'm going to keep the length in HL. It's the easiest way to increment it. I don't have to do a 2-byte increment. HL can be done a 2-byte increment just with the increment X instruction, of course. All right, so here is the read loop. I wait for a character. I bring it in, store it indirect by D, and increment the pointer, increment the length, and then I store the new length in this variable length, so we always have the latest value for length in that variable. And then go back to the loop. It'll just stay here forever because it has no idea how long the data is that's coming in. Now, once I do that file send on the PC in the emulator, in the terminal emulator, of course I can see when it's done. And at that point, I'm ready to record the tape. So all I have to do is hit record on the tape, and then I push reset, raise reset on the front panel. In the 8080, a reset begins execution from address 0. So it jumps out of this loop and goes to 0. In 0, I put out the message writing tape, and then I start writing it. And again, this is just going to loop through the data I just read in, but now we know what the length is because that was determined as we read it in. And then when it's all done, it writes a message saying the tape has been written, and then it just sits here in a loop and dies. If you want to write more tapes, I just stick in another tape and hit reset. It would jump back here to 0 and write the next tape again, of course. All right, so I've got a quick and dirty, it's not meant to be a pretty program, way to create that tape. So at this point, I then have the bootable tape that I showed in the demos, and that's it. So some of you may be wondering, well, what about actually just generating audio from the computer, not using the tape deck at all? Some of us like to do that. And I've done that a lot in the past with the 300 baud Kansas City standard or the 300 baud Altair standard. I've written programs that take data and generate a WAV file, so no actual media involved at all. However, that did not work well at all with the cuts format. And that's because it's not really frequency based, it's more timing based. And maybe in the next video, where I'm going to try to make a cuts interface out of my Altair clone cassette modem that you've seen in other videos, I'll demonstrate more or explain more why that's the case. But because it's not really frequency domain, it's very important that the waveform isn't altered much. But unfortunately, the DAC I have in this machine, the audio DAC that generates, takes a WAV file and creates an output audio waveform, it distorts it quite a bit. When I look at it on an oscilloscope, it's quite different than what I see the waveform in like a sound editor where it looks perfect. And that's because it's trying to make it sound good for the ear or trying to make MP3s, etc. sound good. I've tried different equalizer settings to narrow the bands at which it's reproducing, but no matter what, it ends up moving edges around enough that the cuts board reading it just isn't happy because it's got all sorts of jitter in the data that it tries to recover from that. So on a different computer or a different audio DAC, maybe an old computer, the tapes I created, well, not the tapes, but the WAV files I created might have worked. But I tried triangular waves and sine waves and square waves even, and then with a low pass after it. But yeah, it just wasn't happy because it again, the audio DAC in this computer and most newer computers fiddles with it enough that it's not going to be a pure replication of the waveform you stuck into it. All right, well, that does it for this video and these two videos about using this cuts board and resurrecting this lost tape operating system. And like I said, I probably am going to do a video trying to make my Altair clone's cassette interface, which is basically just a modem, be able to write and read this 1200 baud cuts format. But that'll be in an upcoming video.